Power supply. In this video, we are going to see the internal functional blocks of power supply. Circuit board of power supply. Step-down transformer, bridge rectifier, filter, regulator. The operation of the power supply by its internal circuit is shown. Linear mode power supply. In this video, we are going to see the internal blocks and the function of linear mode power supply. The linear mode power supply consists of step-down transformer, bridge rectifier, filter and regulator. An AC input is given to the step-down transformer. The signal is rectified by the bridge rectifier circuit, filter circuit to remove the ripple component, and regulator circuit gives the regulated DC signal as output. Thus, the regulator, that is constant DC output, is getting from the DC power supply. The input and output waveform of different circuits are shown here. Switch mode power supply, SMPS. Let us see about the switch mode power supply. The switch mode power supply is used in computer. The switch mode power supply, SMPS, is an electronic power processing unit that has a built-in switching regulator. It converts the unregulated AC input from the mains or DC input voltage to a regulated DC output voltage, which is given to the computer peripherals like CPU. This is SMPS. It finds an application in laptops, scanners, mobiles, zip drives, hubs, printers, TV receivers, computers, VCRs, and so on. SMPS has several features of switching regulators: high conversion efficiency, light in weight and compactness, electrical isolation of load from source, lower ripple, provides several isolated outputs from a single voltage input. The difference between the linear mode and the switch mode power supply is shown in the table. Application of rectifier in power adapters. In this video, we are going to see about the use of rectifiers in power adapters. The function of the rectifier is used to convert AC current to DC current. Many electronic gadgets we use in our houses require DC power. For instance, laptop, mobile phone, computer, etc. require DC power to operate. But in our homes, we get AC power supply. Therefore, rectifier is required to convert AC power into DC power. Application of rectifier in UPS. The purpose of rectifier in uninterrupted power supply, that is UPS, is shown in this video. In computer and electronic system, loss of power will cause the irretrievable loss of data and damage the system. To avoid the loss of data and damage of the system, an uninterrupted power is used during the time of power failure. This is the internal circuit board of UPS. The highlighted area is the rectifier section. This is the block diagram of UPS board. The AC main supply is given to the rectifier. The rectifier is used to convert the AC voltage into DC voltage. Circuit connection of half-wave rectifier. In this video, we are going to see the breadboard connection of half-wave rectifier. Primary winding of the transformer AC supply is given to the primary winding. It is the step-down transformer. Secondary winding. The low voltage output from the secondary winding of the transformer is given to the half-wave rectifier circuit. Here, RL is resistive load. The half-wave rectifier is used to convert alternating voltage or current into pulsating voltage or current for 1/2 cycle period of the input cycle. Diode, resistor, rectifier output. The input signal and the rectifier output signal are shown in the CRO display. Half-wave rectifier. In this video, we are going to see about the operation of half-wave rectifier. A single diode acts as a half-wave rectifier. The AC supply to be rectified is applied in series with the diode and load resistance RL. Generally, AC supply is given through a transformer. The use of transformer permits two advantages. Firstly, it allows us to step up or step down the AC input voltage as the situation demands. Secondly, the transformer isolates the rectifier circuit from power line and thus reduces the risk of electric shock. The AC voltage across the secondary winding AB changes polarities after every half cycle. During the positive half cycle of input AC voltage, end A becomes positive with respect to end B. This makes the diode forward biased and hence it conducts current. During the negative half cycle, end A is negative with respect to end B. Under this condition, the diode is reverse biased and it conducts no current. Therefore, current flows through the diode during positive half cycles of input AC voltage only. It is blocked during the negative half cycles. In this way, current flows through load RL always in the same direction. Hence, DC output is obtained across RL. Input and output waveforms. Advantages. Circuit is very simple and occupies less space. Less cost. Disadvantages. Low output voltage VDC is equal to 0.318 Vm. Rectification efficiency is low, 40.6%. Ripple factor is high, 1.21. DC saturation of transformer core results in hysteresis loss and production of harmonics in the power supply. Suitable only for very low power applications. Circuit connection of full wave rectifier. In this video, we are going to see the breadboard connection of full wave rectifier. Primary winding of the transformer, the AC supply, is given to the primary. Secondary winding of the transformer. The full wave rectifier is connected as shown in this diagram. The full wave rectifier converts the alternative voltage or current into pulsating voltage or current during both the half cycles of the input signal. There are diodes and resistors. The input signal and the rectifier output signal are shown in the CRO display. Working of full wave rectifier. In this video, we are going to see about the working of full wave rectifier. A full wave rectifier is an electronic circuit which converts AC voltage into pulsating DC voltage using both half cycles of the applied AC input voltage. Construction. Full wave rectifier consists of a transformer, two semiconductor diodes and a load resistor RL. The secondary windings of a transformer is center tapped. The two voltages V1 and V2 fed to the two diodes are equal in magnitude but opposite in 180 degrees phase difference. One end terminal A of the transformer secondary is connected to the anode of diode D1 and the other end terminal B is connected to the anode of diode D2. The load resistor RL is connected between the center tap C of the secondary winding and interjunction of two cathodes of diode D1 and D2. Working. During positive half cycle of the AC input voltage, terminal A is positive potential, C is at zero potential and B is at negative potential. This makes the anode of the diode D1 positive with respect to cathode. Now the diode D1 is forward biased and diode D2 is reverse biased. Therefore, the diode D1 conducts and at the same time diode D2 remains non-conducting. During the negative half cycle of the AC input voltage, terminal A is negative potential, C is at zero potential and B is at positive potential. This makes the anode of the diode D2 positive with respect to cathode. Now the diode D2 is forward biased and diode D1 is reverse biased. Therefore, the diode D2 conducts and diode D1 remains non-conducting. Input and output waveforms. Input voltage waveform. Output voltage waveform when D1 is conducting. Output voltage waveform when D2 is conducting. Combined output voltage waveform. Load current waveform. Advantages. High output voltage than half wave rectifier VDC is equal to 0.637 Vm. Rectification efficiency is high, 81.2%. Ripple factor is low, 0.421. DC saturation of the core is avoided. Disadvantages: cost is high when compared to half-wave rectifiers. It is expensive to manufacture a center-tapped transformer which produces equal voltages on each half of the secondary windings. Higher peak inverse voltage (PIV) rated diodes are necessary for the operation, which increases the cost. Circuit connection of bridge rectifier. In this video, we are going to see the breadboard connection of bridge rectifier. The AC supply is given as the input to primary winding of transformer. Secondary winding. Connections are made as shown. Bridge network. Bridge rectifier with 4 electrical arms. Input signal to one of the diagonals. Output signal from other diagonal. The input signal and the rectifier output signal are shown in the CRO display. Application of bridge rectifier in power supply. In this video, we are going to see about the application of bridge rectifier in power supply. This is 5-volt DC laboratory power supply. The internal circuit board of power supply is shown. Bridge rectifier network. The input sine signal is given to the bridge rectifier circuit and rectifier output signal is obtained. Bridge rectifier. In this video, we are going to see about the constructions and working of bridge rectifier. A bridge rectifier is an electronic circuit which converts AC voltage into a pulsating DC voltage using both half cycles of the applied AC voltages. Construction. Bridge rectifier consists of the transformer core semiconductor diodes and a load resistor RL. The AC voltage to be rectified is applied across one diagonal of the bridge through a power transformer. The load resistor RL is connected across the other diagonal of the bridge. Working. When the AC voltage is applied to the input circuit, the end terminals A and B of the transformer secondary becomes positive and negative alternately. During positive half cycle of the AC input voltage, terminal A is positive with respect to terminal B. In this situation, diodes D1 and D3 are forward biased, whereas diode D2 and D4 are reverse biased. Therefore, diode D1 and D3 conduct and a current flows through the load resistor RL. The current produces a voltage drop across RL. During the negative half cycle of the AC input voltage, terminal B is positive with respect to terminal A. In this situation, diode D2 and D4 are forward biased, whereas diode D1 and D3 are reverse biased. Therefore, diode D2 and D4 conduct and a current flows through the load resistor RL. The current produces a voltage drop across RL. Input and output waveforms. Input voltage waveform. Output voltage waveform when D1 and D3 is conducting. Output voltage waveform when D2 and D4 are conducting. Combined output voltage waveform. Load current waveform. Advantages. The need of center-tapped transformer is eliminated. The output is twice that of the center-tap circuit for the same secondary voltage. The peak inverse voltage PIV is 1/2 that of the center-tap circuit for same DC output. Disadvantages. It requires 4 diodes. The load resistor and the source have no common point. 2 diodes in series conduct during each half cycle of the AC input. It increases the total voltage drop and losses. Application of bridge rectifier. An application of bridge rectifier is shown in this video. In today's world, most of the electronic appliances need DC voltages from 3 to 12 volts for operation. An adapter is a device which is used to convert high AC voltages to low DC voltage by the help of a transformer and a bridge rectifier. Adapters come in various shapes, sizes and configuration depending on the use. In some cases, adapters are used to provide power to electronic appliances like video games, modems, etc. And in some cases, they are used to charge the primary battery of the electronic device and also act as alternate power source like mobile chargers, laptop chargers, cell chargers, etc. Comparison of half-wave and full-wave bridge rectifier. In this video, the comparison table of half-wave and full-wave bridge rectifier is shown. Types of rectifiers. Number of diodes. Ripple factor. TUF. Transformer utilization factor. And efficiency in percentage. For half-wave rectifier, number of diode is 1. Ripple factor is 1.21. Transformer utilization factor is 0.286. Efficiency is 40.6%. For bridge rectifier, number of diodes is 4. Ripple factor is 0.482. Transformer utilization factor is 0.81. Efficiency is 81%. Problem to calculate ripple factor, gamma. Determine the peak-to-peak ripple voltage and the ripple factor for a bridge rectifier using capacitor input filter. The load resistance is 2 kilo ohms, while the DC voltage across the load is 12 volts. Assume supply frequency to be 50 Hz and ideal diodes. The capacitor of 100 microfarad is used in the filter circuit. Given data, load resistance RL is equal to 2 kilo ohms. DC output voltage EDC is equal to 12 volts. Frequency F is equal to 50 Hz. Capacitance C is equal to 100 microfarad. To determine the peak-to-peak ripple voltage and the ripple factor for a bridge rectifier using capacitor input filter. Solution. VR is equal to EDC by 2 FCRL is equal to peak-to-peak ripple voltage. That is, VR is equal to 12 by 2 into 50 into 100 into 10 to the power of minus 6 into 2 into 10 to the power of 3 is equal to 0.6 volts. The ripple factor is gamma is equal to 1 by 4 root 3 FCRL, where F is equal to 50 Hz, C is equal to 100 microfarad. 100 microfarad is equal to 100 into 10 to the power of minus 6. RL is equal to 2 kilo ohms. 2 kilo ohms is equal to 2 into 10 to the power of 3. Gamma is equal to 1 by 4 root 3 into 50 into 100 into 10 to the power of minus 6 into 2 into 10 to the power of 3. Gamma is equal to 0.0144, that is 1.44%. Problem to calculate ripple voltage V gamma. A full wave rectifier is operated from 50 Hz supply with 120 volt RMS. It is connected to a load drawing 50 milliamps and using 100 microfarad filter capacitor. Calculate the DC output voltage and the RMS value of ripple voltage. Also calculate the ripple factor. Given data: supply voltage ES RMS is equal to 120 volts. Frequency F is equal to 50 Hz. DC current IDC is equal to 50 milliamps. Capacitance C is equal to 100 microfarad. To find DC output voltage EDC, RMS value of ripple voltage VR RMS and ripple factor gamma. Solution: we know that ESM is equal to root 2 ES RMS. ESM is equal to root 2 into 120 volts. ESM is equal to 169.7056 volts. EDC is equal to ESM minus IDC by 4FC. Substitute the values of ESM, IDC, F and C in the above equation. After simplification, we get the final value of EDC as 167.2056 volts. Therefore, the DC output voltage EDC is equal to 167.2056 volts. Then, to calculate RMS value of ripple voltage, we know that VR RMS is equal to IDC by 4 root 3 FC is equal to 50 into 10 to the power of minus 3 by 4 root 3 into 50 into 100 into 10 to the power of minus 6, which is equal to 1.4433 volts. Therefore, the RMS value of ripple voltage VR RMS is equal to 1.4433 volts. The ripple factor gamma is equal to VR RMS by EDC. Substitute the values of EDC, VR RMS in the above equation. Therefore, the ripple factor gamma is equal to 8.63 into 10 to the power of minus 3. Finally, we get EDC is equal to 167.2056 volts. VR RMS is equal to 1.4433 volts. Gamma is equal to 8.63 into 10 to the power of minus 3. Problem to calculate load voltage VL. A full wave rectifier uses a center tap transformer
whose turns ratio to half secondary is 10:1 and is supplied with 230 volts at 50 Hz. The load resistance is 50 ohms. Calculate the load voltage and the ripple voltage. Given data: primary RMS value EP RMS is equal to 230 volts. Frequency F is equal to 50 Hz. Transformer's turns ratio N1:N2 is equal to 10:1. Load resistance RL is equal to 50 ohms. To find, calculate the load voltage and the ripple voltage. Solution: ratio of EP RMS by ES RMS is equal to N1 by N2 is equal to 10 by 1. Therefore, ES RMS is equal to EP RMS by 10, which is equal to 230 by 10 is equal to 23 volts. Therefore, ESM is equal to root 2 ES RMS is equal to root 2 into 23, which is equal to 32.5269 volts. Therefore, IM is equal to ESM by RL. Substitute the ESM and RL values in the above equation and find the IM value. Therefore, IM is equal to 0.6505 amps. Therefore, IDC is equal to 2Im by pi, which is equal to 2 into 0.6505 by 3.14, which is equal to 0.4141 amps, and EDC is equal to IDC RL is equal to 0.4141 into 50, which is equal to 20.7072 volts. Ripple factor is equal to 0.48 for full wave without filter. Problem to calculate capacitance. In a half-wave rectifier circuit fed from 230 volts, 50 Hz means it is desired to have a ripple factor gamma less than or equal to 0.005. Estimate the value of the capacitance needed IL is equal to 0.5 amps. Solution: given data, RMS value of secondary voltage ES RMS, which is equal to 230 volts. Frequency F is equal to 50 Hz. Ripple factor gamma less than or equal to 0.005. Load current IL, which is equal to 0.5 amps. To find, capacitance C is equal to what? Formula used: gamma is equal to 1 by 2 root 3 FCRL. RL is equal to EDC by IL is equal to ESM by pi IL. ESM is equal to root 2 ES RMS. Calculation. First, we have to find the ESM value. ESM is equal to root 2 ES RMS is equal to root 2 into 230. ESM is equal to 325.269 volts. Then find the RL value. RL is equal to EDC by IL is equal to ESM by pi IL. RL is equal to 325.269 by pi into 0.5. RL is equal to 207.072 ohms. To find the capacitance value, substitute the ESM and RL values in the equation. Gamma is equal to 1 by 2 root 3 FCRL. C is equal to 1 by 2 root 3 F gamma RL. C is equal to 1 by 2 root 3 into 50 into 0.005 into 207.072. C is equal to 5.576.
Problem to calculate ripple voltage, V gamma. A full wave rectifier has a load of 2 kilo ohms. The AC voltage applied to the diode is 200, 0, 200 volts. Assuming ideal diodes, calculate 1. Average DC current, 2. Average DC voltage, 3. Ripple voltage. If the capacitor of value 500 microfarad is connected across the load, what is the new value of the ripple voltage? Assume F is equal to 50 Hz. Given data, load resistance RL is equal to 2 kilo ohms. RMS value of secondary voltage ES RMS is equal to 200 volts. Frequency F is equal to 50 Hz. Capacitance C is equal to 500 microfarad. To find average DC current IDC, average DC voltage EDC, ripple voltage V gamma. Ripple voltage V gamma at capacitance C is equal to 500 microfarad. Solution. Average DC current IDC ESM is equal to root 2 ES RMS. Therefore, ESM is equal to 282.8427 volts. IM is equal to ESM by RF plus RS plus RL. Therefore, IM is equal to 0.1414 amps. IDC is equal to 2 IM by pi. After simplification of this equation, we get IDC is equal to 0.09 amps. Average DC voltage EDC. EDC is equal to IDC into RL. By substituting IDC and RL value, we get EDC is equal to 180 volts. Ripple voltage V gamma for full half-wave rectifier is equal to ripple factor is equal to 0.48. Gamma is equal to V gamma RMS by EDC. Therefore, V gamma is equal to gamma into EDC. That is equal to 86.4 volts. If capacitor filter of C is equal to 500 microfarad is used, then gamma is equal to 1 by 4 root 3 FCRL. Therefore, gamma is equal to 2.8867 into 10 to the power of minus 3. Therefore, the new ripple voltage V gamma is equal to 0.5196 volts. Problem to calculate peak rectified voltage ESM. A full wave rectifier circuit uses a capacitor filter with 500 microfarad capacitor and provides a load current of 200 milliamps at 8% ripple. Calculate DC voltage across filter capacitor, the peak rectified voltage obtained from 50 Hz supply. Given data, capacitance C is equal to 500 microfarad. Load current IL is equal to 200 milliamps. Ripple factor is equal to 8% and frequency F is equal to 50 Hz. To find DC voltage EDC is equal to and maximum value of AC voltage ESM is equal to what? Solution. Ripple factor is equal to 1 by 4 root 3 FCRL is equal to 1 by 4 root 3 into F into C into EDC by IL. Therefore, ripple factor is equal to IL by 4 root 3 FCE DC. Therefore, EDC is equal to IL by 4 root 3 into F into C into RF is equal to 200 into 10 to the power of minus 3 by 4 root 3 into 50 into 500 into 10 to the power of minus 6 into 8 by 100. Therefore, EDC is equal to 14.43 volts. Now, EDC is equal to ESM minus IDC by 4FC. From this we can write, therefore, ESM is equal to EDC plus IDC by 4FC. Therefore, ESM is equal to 16.43 volts. Problem to design a half-wave rectifier. Design a suitable half-wave rectifier with capacitor filter to obtain DC voltage of 10 volts DC with a ripple below 0.1 at a standard load of 10 kilo ohms. Given data, for a single-phase half-wave rectifier, F is equal to 50 Hz. DC voltage V DC is equal to 10 volts. Ripple factor is equal to 0.1. Load resistance RL is equal to 10 kilo ohms. To find, design a suitable half-wave rectifier with capacitor filter. Solution. For half-wave rectifier, ripple factor is equal to 1 by 2 root 3 FCRL. 0.1 is equal to 1 by 2 root 3 into 50 into C into 10 into 10 power 3. C is equal to 1 by 2 root 3 into 50 into 0.1 into 10 into 10 power 3. Therefore, C is equal to 5.78 into 10 power minus 6 farads. From this, select C is equal to 5 microfarads. Also, EDC is equal to 10 volts. We know that EDC is equal to ESM minus IDC into 1 by 2FC, where IDC is equal to EDC by RL, which is equal to 10 by 10 into 10 power 3, which is equal to 1 milliamps. By substituting all the values in the equations, EDC is equal to ESM minus IDC into 1 by 2FC. We can get the value of ESM. After the simplification, we get the maximum AC voltage as ESM is equal to 12 volts. Then, select the diode with PIV greater than or equal to ESM 12 volts and ES RMS is equal to ESM by root 2, which is equal to 12 by 1.414, which is equal to 8.48 volts. Voltage rating of transformer is 0 to 8.48 volts. From the obtained value, we can design the half-wave rectifier as shown here. Problem to design a full-wave rectifier. Design a full-wave rectifier with a capacitor filter to meet the following specifications. DC output voltage is equal to 15 volts, load resistance 1 kilo ohms, RMS. Ripple voltage on capacitor is equal to less than 1% of DC output voltage. Assume the AC supply voltage as 230 volts, 50 Hz. Given data, DC output voltage EDC is equal to 15 volts. Load resistance RL is equal to 1 kilo ohms. RMS ripple voltage on capacitor is equal to less than 1% of DC output voltage. Therefore, VRRMS is equal to 1% of EDC. To design a full wave rectifier with a capacitor filter. Solution. Now, VRRMS is equal to gamma into EDC, where gamma is the ripple factor. That is, VRRMS is equal to 1% of EDC. Therefore, gamma is equal to 0.01. But we know that gamma is equal to 1 by 4 root 3 FCRL, where F is equal to 50 Hz for full wave rectifier. By substituting the known value in the above equation and simplifying, we get the capacitance value. Therefore, C is equal to 288.675 microfarads. Then, choosing standard capacitance value, C is equal to 300 microfarads. EDC is equal to ESM minus IDC by 4 FC, and IDC is equal to EDC by RL, where IDC is equal to VDC by RL is equal to 15 by 1 into 10 to the power of 3. Therefore, 15 is equal to ESM minus 15 by 1 into 10 to the power of 3 into 1 by 4 into 50 into 300 into 10 to the power of minus 6. By simplifying the equation, we get the maximum AC input voltage across each half of secondary winding, that is ESM, which is equal to 15.25 volts. Thus, secondary maximum voltage from transformer, that is ESM, is 15.25 volts and primary RMS value, that is EPRMS, is 230 volts. EPM is equal to root 2 EPRMS. EPM is equal to root 2 into 230. EPM is equal to 1.41421 into 230. EPM is equal to 325.2691 volts. For the input transformer, EPM by ESM is equal to N1 by N2, where EPM is equal to 325.2691 volts. ESM is equal to 15.25 volts. Therefore, N1 by N2 is approximately equal to 22:1 for each half of secondary. As it is, center tap total turns ratio is N1:2 N2. The PIV rating of diode must be greater than 2 ESM, that is 2 into 15.25, which is equal to 30.5 volts. The voltage rating of secondary transformer is ES RMS to 0 to ES RMS. That is 15.25 by root 2 to 0 to 15.25 by root 2. That is 10.7833 to 0 to 10.7833 volts. By using the voltage rating of secondary transformer, we find the primary RMS value, that is EPRMS, is equal to 220 volts. So, turns ratio of transformer is N2 by N1 is equal to ES RMS by EPRMS is equal to 7.1935 by 220, which is equal to 0.0327. Therefore, N1:N2 is 30.583:1. Assume full wave bridge rectifier. The designed power supply is shown here.